All right, let's dive into a really cool piece of cryptographic magic. It's a protocol called MuSig2, and it has this incredible secret. It can take digital signatures from a whole bunch of different people and make them look like they came from just one person. The question is, how on earth is that even possible?
I mean, really think about that. How can you take three totally separate signatures and combine them so that they look exactly like a single signature? It sounds like some kind of illusion, a cryptographic sleight of hand, but believe it or not, that's exactly what we're going to unpack.
So to really get why this is such a game changer, you have to understand the old way of doing things. You know, on blockchains, having multiple people sign off on a transaction is a super common security step. But traditionally, it's been messy. Every single signature has to be recorded right there on the blockchain, which just eats up space, jacks up the fees, and honestly isn't great for privacy.
And when you put them side by side, the difference is just wow. The old way leaves a big public footprint of every signer, which means higher fees and way less privacy. But with MuSig2, all that complexity gets squashed down into one neat, tidy signature before it ever hits the chain. And the result? Lower fees, way more privacy, and the whole thing is just faster and more efficient.
And this is where MuSig2 enters the picture. It is such an elegant solution to this whole multi-signature headache. You can think of it as the art of cryptographic collaboration, letting a group of people act as a single entity, all without leaving a trace. It's brilliant.
So here's the core idea. MuSig2 lets multiple signers work together to create a single standard signature. Now, the most important word on this slide is indistinguishable. The final signature looks identical to one made by a single person. Seriously, whether it's one signer or 10, to the outside world it looks exactly the same. That is a massive leap forward for both privacy and efficiency.
Okay, so how does this actually work in the real world? Let's follow the example from the source code itself and meet our three collaborators, Alice, Bob, and Carol. Their mission, should they choose to accept it, is to sign one digital message together.
The whole process is surprisingly quick. It only takes 2 rounds of communication. This first round is like the handshake. It's all about preparation, where everyone gets their secret ingredients ready to go before the real magic starts.
So round 1 has 4 simple steps. First, Alice, Bob, and Carol each generate their own secret and public keys. Pretty standard stuff. Then they share only their public keys with each other, and those keys get mathematically combined into one single key for the whole group. After that, they each generate something called a nonce, which is just a secret number they'll only use this one time. And finally, just like with the keys, they share their public nonces, and those get combined too.
And if you look at the code, this is that moment of aggregation. This function here takes the individual public keys from Alice, Bob, and Carol and just cryptographically merges them. The output is a single, aggregate public key that now represents the entire group as one.
So what in the world is a nonce? It's a critical piece of the puzzle. It literally just means number used once. The best way to think about it is like a disposable, single-use security token. Each person generates a totally fresh, random nonce for every single signing session. This makes sure that no 2 sessions are ever the same, which is absolutely vital for preventing certain kinds of attacks.
And here's what that nonce generation looks like in the code for Alice. Now, notice how she's using her own keys, but she also includes the group's aggregate key and the message they're signing. This is super important because it binds her contribution specifically to this group and this message. Behind the scenes, Bob and Carol are doing the exact same thing.
Okay, prep work is done. All the ingredients are on the counter, the group's key is ready, and everyone has their unique, one-time use nonce. Now we're ready for round 2, forging the actual signature. This is where we combine all the flavors. This round is much more direct. First, each person uses their secret stuff, their secret key and secret nonce, to create what's called a partial signature. It's their unique piece of the puzzle. Next, they share those partial signatures, and they get combined into one final signature. And then, the moment of truth. Anyone can verify that signature against the group's public key to prove it's legit. So here, we see Alice calling the signed function. She plugs in her secret nonce and her secret key, and out pops her partial signature. This is her individual contribution, her voice in the final product. But on its own, it's not complete. And this is the final combination. This function, partial SIGAG, takes the puzzle pieces from Alice, Bob, and Carol and mathematically merges them. What comes out the other side is the single final signature that represents the whole group's consensus.
And this, right here, is the ultimate payoff. This line of code asks a very simple question. Does this final combined signature correctly validate our message against the group's public key? And the answer is true. It worked. The combined signature is cryptographically sound. The magic trick was a success.
So we've just gone deep into the how, but let's zoom back out to the why. Why does all this cryptographic gymnastics actually matter? Well, the real-world impact is huge. It really all boils down to major upgrades in privacy, efficiency, and cost. First, you get incredible privacy. Because a MuSig2 signature looks just like any other standard signature, nobody looking at the blockchain can tell if one person signed it or 20 people signed it. Second, efficiency. All the complex back and forth happens off-chain, so the final record that gets stored is tiny. And of course, that efficiency leads directly to lower costs. Less data on the blockchain means lower transaction fees, and that's a huge win for any system.
But wait, there's more. The protocol has one more really clever trick up its sleeve. It's an optional feature called deterministic signing, and it adds a whole other layer of flexibility to the process.
So get this. It actually changes the two-round flow we just walked through. Instead of everyone having to prepare their nonces all at the same time, one signer, let's say Carol, can just hang back. She can wait to get the public nonces from Alice and Bob first, and then create her own. This can actually make coordinating the whole signing ceremony a lot simpler in some cases.
To pull this off, Carol uses a special deterministic sign function. She inputs the combined nonce she got from Alice and Bob, and this function brilliantly outputs both her own public nonce and her partial signature all in one go. It's just a really clever optimization.
So, by making many signatures look like one, MuSig2 gives us better privacy, higher efficiency, and lower costs. It's a really powerful idea that proves digital identity can be both incredibly secure and deeply collaborative. And that leaves us with one final question to chew on. If we can seamlessly combine digital keys like this, what's next for collaborative security?